When the processes are kept in a ready queue, we say that the process is ready for execution. So CPU considers only those kind of processes for execution. A thread is defined as a flow of execution through the process code. Operating system is the one which is responsible for switching over from one process to another process. A warm welcome to the System Software and Operating Systems. In this you will have the process schedulers. Here we have three different types of schedulers. One is long-term scheduler, second one is short-term scheduler, third one is medium-term scheduler. What is the meaning of long-term scheduler? Suppose if the job requires more time, then it is called as a long-term scheduler. If it takes very less time, then it is called as a short-term scheduler. If it takes an average of time, then it is called as a medium-term scheduler. So if that is the case, let me distinguish one from the other. It is a job scheduler, it is a CPU scheduler, it is a process swapping scheduler. Please keep this in your mind. We have a job scheduler which takes more time, is called as a long-term scheduler. The CPU, since the CPU cycles are very fast, so it takes less time to execute the job. So we have the CPU scheduler. When there is a need of one of the job needs to be brought from secondary memory to the primary memory and primary memory to the secondary memory. So there is a need of swapping which requires an average term scheduler. So we have these schedulers here. Then, as I have already told you, speed is lesser than the short-term scheduler. Speed is fastest among the two. That is, among all these two, this is fastest. Speed is in between both short and long-term scheduler. That is the average term scheduler. It controls the degree of multi-programming. That means multiple programs can be executed, which can be controlled by using the long-term scheduler, which is less control over the degree of multi-programming, which has more control over the degree of multi-programming. It has reduced the degree of multi-programming. Then, it is almost absent or minimal in time sharing system. That is, when the time quantum is fixed, Q1 is allotted to one of the job, Q2 is another allotted to another job, quantum 3 is allotted to another job. So we have a time quantum, fixed time quantum. So in all these cases, it is very minimal in case of time sharing operating system. Then it is also minimal in case of time sharing operating system. It is a part of time sharing operating system. So we have the fifth differences. It selects the processes from the pool and loads them into memory for execution. As I have already told you that this selects the processes which are ready to execute. We have already shown you that the queue consists of different queues, that is ready queue and device queue and waiting queue. When the processes are kept in a ready queue, we say that the process is ready for execution. So CPU considers only those kind of processes for execution. So it is very less time. So medium term scheduler requires it can reintroduce the process into memory and execution can be continued. That means it needs to take the process from the waiting queue to the ready queue than to the execution. So that is why it requires more time in comparison with the CPU scheduling. That means the short-term schedulers. If that is the case, cooperating process. What is the meaning of cooperating process? When one process is dependent on another process, we say that it is a cooperating process. What about the independent process? We have another type of process called as independent process. Process P1 and P2. The resources assigned to P1 is not at all required for P2. So these processes are not relying on this process. So these two processes P1, P2 are called as an independent process. But in this case, we have R1 and R2 part of the resources assigned to P1 is required for P2. So P1 is relying on P2 and P2 is also relying on P1 for part of the resources. That's why it is called as a cooperating process. These are called as an independent process. The same thing is explained here. Any process that does not share data with others is called as an independent. Otherwise, the process is called as a cooperating process. Cooperation is done to provide information sharing, computational speedups, that is the information sharing, resources in terms of computational speedups, modularity and convenience are the types of resources which is shared among the cooperation processes. There should be some mechanism to inter-process communication and to synchronize their actions. That means in order to communicate between P1 and P2, we must have some mechanism to allow these processes to interact with each other. In order to make them interact with each other, we must have a medium there that is provided by shared memory concept, as I have already explained in the previous session. And the other one is message passing system, message passing method or system. So this is how the processes are tackled by the operating system. The best way to see the cooperation is by seeing an example of the consumer-producer problem. What is the meaning of consumer-producer problem? Consumer is the module which requires certain data, which consumes some amount of data, where the producer is the module that is going to produce some data to the user. User is the module is going to utilize the module produced by the producer. So we are going to consider this as a consumer and this as a producer. So this is one of the best classical examples of operating system that defines the cooperating processes. So the inter-process communication, IPC, is a set of programming interfaces that allow a program to coordinate among different program processes that can run concurrently in an operating system. That is, synchronization is needed. This allows a program to handle many users' requests at the same time. Multiple requests are serviced at the same time. Since even a single user request may result in multiple processes running in the operating system on the user's behalf, the processes need to communicate with each other. That means one single user request may result in multi-processes. That is, user 1 is there going to produce multiple requests. That is R1, R2, R3, R4, R5. If that is the case, we have multiple requests. All these requests are processed by process P1, P2, P3, P4, P5. We have all these processes. All these processes must be executed. In order to execute these processes, there must be some interaction among these processes. In order to allow them interact with each other, there must be some mechanism called inter-process communication. Then, threads. A thread is defined as a flow of execution through the process code. This is very, very important. Each of the process P1, process P2 is having multiple threads. For example, T1, T2, T3, T4, T5, T6. We have these threads here. How many threads are there in P1? We have 3 threads. How many threads are there in P2? We have 3 threads. So each of these processes can do multiple tasks at the same time. So that is how we are going to do that. Threads. Each thread belongs to exactly one process, and no thread can exist outside a process. Each thread represents a separate flow of control. What does this mean? Each thread belongs to exactly one process, not more than that. If that is the case, we have the relationship called one-to-one, one-to-many, many-to-many model. All these are models designed in operating system to work with threads. Process. The difference between process and a thread. A process is a lightweight or resource intensive, whereas thread is a lightweight taking lesser resources than a process. Process switching, that means processor switches from one process to another process that needs interaction with operating system. That means operating system is the one which is responsible for switching over from one process to another process. That is the importance of process. If I come to the threads, thread switching does not need to interact with operating system because these threads are available within a process. So process can manage that with the help of a data structure process control block, which is the third difference. In multiple processing environments, each process executes the same code but has its own memory and file resources. All threads can share the same set of open files and child process because we will be having only one process which is having multiple threads. If one process is blocked, then no other process can execute until the first process is unblocked. Plus, see to it here, when one thread is blocked and waiting, a second thread can do the same job and run. Please observe this carefully here. When one process is blocked, other process cannot execute until the first process is unblocked. But in case of threads, if one of the thread is blocked, another thread can take the job of another thread and work as an alternative to this, so that there is no stopping of execution. Then we have multiple processes without using the threads use more resources. If I do not have threads within a process, that consumes more number of resources. But multiple threaded processes use fewer resources. That is the main thing. In multiple processes, each process operates independently of the other. That means one of the processes can operate independently with other without relying on the resources of other processes. But in case of this thread can read, write or modify another thread's data. That means only cooperating operation is needed in case of threads, because there are multiple threads within a same process. But it is not the case with process. Process can also be an independent process or a cooperating process, but a thread is called as a cooperating thread. So we have types of threads here. One is user level threads and the other one is kernel level thread. These user level threads are generated by users. Kernel threads are generated by operating system. So there must be some interaction between kernel level thread and the user level thread, which indirectly communicates and helps the users to interact with the operating system. That means we have a user threads like this. The thread management kernel is not aware of the existence of threads. That means the thread library contains code for creating and destroying threads. We have a library of threads, pool of threads. These pool of threads are responsible for creating, destroying the threads. As soon as the work is over, it is destroyed. Whenever it is required, it is created. That is how we are going to do that. You people might have seen that multiple threads are running. If you come across the cutting edge technologies and the scientific computing technology like MATLAB, whenever you want to execute the programs simultaneously, we have an option called pair pool. That is, a pool of threads are created. Then these threads are responsible for executing the program simultaneously at the same time. So that is also one of the important points you need to observe there, where the software is taking the effort of operating system and doing the operations of it. Threads for scheduling thread execution and for saving and restoring the thread contexts. So if you look at this diagram, you will clearly understand that process P1 is having T1, T2, T3. Process P2 is having T4, T5, T6 thread library we have. We have CPUs here, multiple CPUs. This is called as a kernel space. This is called as a user space. So the process interacts with operating system through the kernel space. The kernel space is operated by operating system. This is operated by users. So there is an indirect interaction between user and operating system. Moving on to the kernel threads, we have thread management is done by the kernel. There is no thread management code in the application area. That means there is no thread management code to manage all these codes in the application area, that is in the user end. It is available only in the operating system. So kernel threads are supported directly by the operating system. Yes. Any application can be programmed to be a multi-threaded. Any program which needs to be executed can be done with the help of a multiple threads. So all these threads within an application area are supported within a single process. That means a single process can do multiple jobs in an operating system because multiple threads are created within a single process. So this is how we are going to do that. The kernel maintains a context information for the process as a whole and for individual threads within the process. Then scheduling by the kernel is done on a thread basis. Kernel performs thread creation, scheduling and management in kernel space. That means in the kernel space you have seen here, the kernel threads are responsible for maintaining the creation of the threads and their management. Then we have kernel threads are generally slower to create and manage than the user threads. Then what is the difference between user level thread and kernel level thread? So user level threads are faster to create and manage, that is slower to create and manage. Implementation is by a thread library is done at the user level. This is done at the kernel level or at the operating system level. User level thread is generic and can run on any operating system, whether it is a Unix, Linux, Windows or any operating system. Kernel level threads are specific to the operating system. That means it is specific to only Windows. It is specific either only to Unix or only to Linux or anything like that. Multi-threaded applications cannot take advantage of multiprocessing. That means multiple threads applications cannot take the advantage of multiple processing at the same time. Whereas kernel routines themselves can take multi-threaded operations. So this is how we are going to work out with process scheduling and process schedulers. These process schedulers are responsible for scheduling by the CPU. So we distinguished the process along with that threads. Thank you very much. Thank you one and all.